Hello, everybody. In this particular video, we're going to be talking about partial differential equations. And normally in these videos, I would say we're going to talk about numerical analysis for the particular topic. But in this case, you might not even know what a partial differential equation is. And so I'm going to go through a derivation that actually gives you your first partial differential equation and hopefully a sense of what a PDE actually is. So what is a PDE? Well, the simplest possible thing to say is that a PDE, partial differential equation, is an equation that relates the partial derivatives of a function to the function itself. But that's kind of a really worthless example or worthless definition if you don't have any examples in mind. So we're going to build what's called the diffusion equation. So take, for example, we've got a number line here, and say we've got particles of gas that are distributed kind of at different densities along this number line. So in some areas, the gas is really dense, and in some areas, the gas is very sparse. Now, what I'm going to do is I'm going to split this into a discrete collection of subintervals, roughly the same size, and we're just going to have a couple of rules. All right, the rules are that 50% of the particles move right, and 50% of the particles move left at any time interval. So we're thinking we make the subintervals, the spatial intervals small enough that the simple Brownian motion of a particle running into another and making it move will force it either into the right subinterval or to the left one. Okay, so they're moving, so say we're here, they're either going to move this way or they're going to move this way with a probability of 50-50. So we're going to call this thing subinterval n. This will be subinterval n plus 1. This will be subinterval n minus 1. And we get some rules, right? If u is the density of the particles, then I could say that u at time t plus delta t at spatial location xn minus u at t spatial location xn. Right, so this is the change in density over time is going to be given to us as, well, let's see here. Half of my particles move to the right, and half of my particles move to the left. So I'm thinking of this as that's going right, that's going left. Now I also get plus half of the particles in from the right, those are the ones coming in from here, and half of my particles coming in from the left. Those are my particles coming in from here. Now, a little bit of rearranging. I've got my change in density over time. I'm going to pull out that 1/2, and I'm just going to do a little bit of clever rearranging. So if I do u at t x n plus 1 minus 2 of u at t x n plus u at t x n minus 1. I've got 2 in the 1/2 here. That makes a 1. That's both of these. And then this one is here. That one is there. So I haven't done anything fancy. But now I'm thinking, I'm in a numerical analysis class. These things look familiar. If I divide this side by delta t, that looks like a time derivative. And if I divide this side by a delta x squared, that looks like a second derivative in space. Oops, I forgot to close my parenthesis. Well, I can't just do that all willy-nilly. So let's multiply out by a delta x squared and divide out by a delta t. So I haven't changed anything in the equation. But what I have now is I have a change in time is equal to 1/2 delta x squared over delta t, gathering those together, times a second derivative in space. And then lastly, what I'm going to say is I'm just going to call that coefficient d and I have a differential equation. So when I came back up here and said a PDE is a differential equation that relates a function and its partial derivatives to each other, well, in this really simple case, the function is the density of these particles, and the differential equation relates the time derivative to the spatial derivative. Now, when I went from here to here, you should have had a little alarm bell going off and said, this is not the same as that. What I'm really thinking here is I want a limit as delta t heads to 0 and a limit as delta x heads to 0. In those limits, these differences become these derivatives. So in those limits, that means I'm moving these little partitions closer and closer and thinking of this as a continuum, not as discrete intervals, and my time intervals are getting smaller and smaller and smaller. That's basically the game in partial differential equations. And here we have our first honest to goodness, good old-fashioned PDE. And this is a guy we're actually going to spend a lot of time solving. This is called the diffusion equation or the heat equation. Okay, in the next videos, we're going to look at other PDEs, and then we're going to look at what it means to solve them numerically. See you there.